Hi everybody, Dr. Rutner here again. We are going to take a look at the pooled variance t-test in this video. So we're going to take a look at the assumptions for the test, how we set up our hypotheses, how we do all our computations, and then how we reach a conclusion. So we'll work an example from start to finish. So looking at pooled variance t-tests, we are looking at trying to compare the difference between the means of two populations, so expressed here as mu1 and mu2. And the way we're going to evaluate that difference is collect some sample data and look at the difference between the means of our two samples. If we find that that sample mean is different enough from our hypothesized population mean difference, then we'll say that that's a statistically significant difference and we'll reject our null hypothesis. Otherwise, we won't. So going through our basic steps of hypothesis testing, just with the difference between two means. We are going to be working in this situation with independent samples. That is where there is no relationship between items in the two different samples that we're going to be looking at. So we're assuming that they were drawn randomly and independently from their populations. Recall from our overview that even once we got into looking at independent samples with two means, there were still two possible tests that we could do, and the choice between those tests rests on whether we can assume that our population variances are equal to one another, in which case we'll do a pooled variance t-test, or not equal to one another, in which case we have to do a separate variance t-test. This video is looking at the pooled variance t-test. There'll be a separate one that looks at the separate variance t-test. But continuing on, assumptions for the pooled variance t-test is that, again, we are working with samples that were randomly and independently drawn for their populations. Then additionally, we also need either to assume that the populations themselves are normally distributed, or that we have sample sizes that are large enough to allow us to assume that the central limit theorem applies and that the sampling distributions are normally distributed. So sample sizes of at least 30. And then also, as we just mentioned, we have to be able to assume that population variances, while we may not know what they are, we do have to at least be able to assume that they're equal to one another. So you should be able to pick up all of this information in your problem statement. If you get into a problem statement and you're not sure if you're able to pick up all this information or not, then typically what you would want to do is state any assumptions that you have to make to use one of the techniques and include that as part of your solution. And so that way, if you give me something and maybe didn't choose the technique I was hoping you would get from a particular problem situation, then at least I'll have some information about why you did make the choice you did, and I can give you credit accordingly. So just a little tip for homework problems and exam problems, that sort of thing. But these are the assumptions that underlie the use of the pooled variance t-test. All right. Now, just want to refresh your memory a little bit on a couple of pieces that we had looked at, or a couple of the items that we had looked at when we first introduced critical value hypothesis testing. We would state a rejection rule in which we would compare a test statistic to a critical value of that statistic based on a specified level of significance. And so we might say something like, we're going to reject the null hypothesis if my test statistic is greater than 1.96 or less than negative 1.645, something like that, depending on how we set up our hypotheses and what that level of significance was. And then we would compute a test statistic. And what I have expressed here is just a general description of the relationships that we use to compute that test statistic. I'm calling it t-stat here, but this would apply for a z-statistic as well. But we're computing that test statistic by taking our sample statistic, subtracting the hypothesized population parameter, and then dividing by the standard error of the distribution that we're working with. So when we were working with just a one sample mean hypothesis test, that computation was x bar minus mu. divided by the standard error, which we typically expressed as sigma over the square root of n, or s over the square root of n if we were working with a t distribution. So just refreshing your memory on the basic relationships that we'd looked at. And the reason I wanted that fresh in your mind is because we're looking at the same basic relationships, even though we're now moving into a two-sample situation. We're still going to take a sample statistic. We're still going to subtract a hypothesized population parameter. We're still going to divide by a standard error. It's just that each one of those terms is now going to be just a little bit more complicated. So let's take a look at those. And so what you see here is, first of all, here is the computation for the test statistic that we're going to use. This is going to be based on our sample data, and we'll compare this to a critical value of t in order to make our rejection decision, our reject, do not reject decision. But let's kind of take it a piece at a time. And so as we look up here, our test statistic now is not going to be just a single mean. It's actually going to be the difference between the two means that we're comparing. Then we're still going to subtract a hypothesized population parameter, but again, not just a single value. That's now going to be the hypothesized difference between our two population parameters. So sample statistic minus population parameter, just a little bit more complicated. And then in the denominator of this relationship that computes our t statistic for us, this is the standard error of the distribution of the difference between these two different parameters. So let's take a look at this because we actually still need to do a few computations. A little more complicated than just taking s over the square root of n here, unfortunately. So the way we compute the standard error is we take something called a pooled variance, and that's what this term is. S squared means that it's the variance. The subscript p indicates that this is a pooled variance across our two samples. Multiply that by 1 over n1, which is the size of sample 1, plus 1 over n2, which is the size of sample 2. Multiply those terms together and take the square root, and that is the standard error of the sampling distribution that we're working with. Now, this pooled variance term is also something that we need to compute, and you can see the formula for the pooled variance down here. We compute that as sample size of sample 1 minus 1 times the variance of sample 1 plus the size of sample 2 minus 1 times the variance of sample 2, and then divide by the size of sample 1 minus 1 plus the size of sample 2 minus 1. And this term that we're dividing by also happens to be equal to the degrees of freedom that we need to use for the t distribution that we're going to be doing for our test. Remember that the t distribution is not just a single distribution, it's actually many different distributions, a whole family of distributions that are defined by their degrees of freedom. Well, when we're working in a two-sample situation and we're able to do a pooled variance t-test, we can compute that degrees of freedom as the sum of the two sample sizes minus 2, and it's just expressed slightly differently in the denominator of this function, but it computes out to be the same number. So these are the formulas that we'll use for our computations. Now let's take a look at an example problem, and we'll see about how we can set up our hypotheses, how we can apply those formulas to do computations, and how we can work this all through. So looking at this problem, plant manager of an office equipment manufacturer is considering two different methods of assembly for a new ergonomic office chair. In order to help decide, he wants to do a little experiment. And so he randomly, or she randomly, selects 25 workers and has them assemble the chairs using method A, all right, whatever method A happens to be, and then randomly selects another 25 workers and has them assemble chairs using method B. We're going to record the assembly times, and those mean times are what we're going to compare to see whether there's a difference between the two. We're told that we can assume that the two populations of assembly times are normally distributed and that they have equal variances. We're going to test at the 0.05 level of significance whether there is a difference in mean assembly time between the two methods. So going back to our roadmap, the first decision we need to make is, well, what kind of a variable are we evaluating here? And in this case, we're comparing assembly times. So that's a numerical variable. So that rules out the z-test for the proportion for us. We're making a comparison between mean assembly times. So that rules out the f-test for two variances. We have got two different randomly selected samples of workers, which are going to give us two different samples of assembly times. We're not told that there's any connection between the workers who are using method A and the workers who are using method B. So even though we've got 25 in each group, we don't have a way to match up a worker from one group with a worker from another group. And so we can assume then that these are independent samples as opposed to paired samples. And just as a side note, had we been told, all right, so hypothetically speaking, instead of being told that we had two groups of 25 workers apiece, if we had had the same group of 25 assemble two different chairs, one using method A and one using method B, then we would have a way to pair those up and we'd be in a paired sample situation. But we weren't told that. We were told that we've got two separate, independent, random samples of workers. So that puts us into the independent t-test situation. And then finally, we're told both that our assembly times are normally distributed and that they have equal variances. So we know we are in the pooled variance t-test because we can make the assumption of equal variances, and we need to know about the normal distribution of the populations because our sample sizes are both less than 30. So going through, kind of picking out all the pieces here, we've got a pooled variance t-test, not surprising since this is the pooled variance section, but that's how I would pick apart this problem statement to make sure that I'm in the right situation here. And so with that, let's start taking a look at how we're going to set this up. Now, I've actually got the write-up for this, my solution for this problem. I've actually got this set up in a document, and rather than copy the document into a set of slides, I decided I would just go ahead and go through this document with you. This document will be posted in PDF form to Blackboard, so you can get your own copy of it and then use it to refer to if you're working on a problem. So I've got the same problem stated here, and then I've also got instructions for three things that we need to do. First of all, we're going to test the hypotheses using the critical value approach. Then we are going to compute a p-value based on our sample data and see whether it confirms the results that we got with the critical value approach. And then finally, we're going to compute a confidence interval for the difference between means and then see whether that confirms what we found out with our critical value hypothesis test. So we're going to work through all three of these, but we will start by stating our hypotheses. And so that's what you see here is hypothesis, the null hypothesis and the alternative hypothesis. And you can see these are stated in terms of the population parameters. I'm using the subscripts A and B to distinguish method A from method B for the assembly times. I like to use meaningful subscripts if I can, because I find it helps keep me from getting confused between what's going on between the two different populations. If I just randomly make them 1 and 2, that gets very confusing. But in this case, what I'm doing is my null hypothesis is that there is no difference between the assembly times. I'm doing a two-tailed hypothesis here because the question was asking me, is there evidence of a difference? And so it's not asking, is there evidence that one takes longer than the other or doesn't take longer than the other? It's just asking, is there evidence of a difference? And so that's the kind of terminology or verbiage that you would look for to recognize that you're in a two-tailed situation. So in this case, A could take longer, B could take longer. Either one of those would cause us to reject the null hypothesis that there is no difference in favor of the alternative that the two are different from one another. The two mean assembly times are different. So there's our hypothesis statements. And then just capturing the information from the problem, we're testing it alpha is 0.05. And in this case, we happen to have 25 assembly times in each of our two samples. Remember that with a pooled variance t-test like this, sometimes those sample sizes will be equivalent, sometimes they won't. They don't have to be equivalent. So moving on, we've already talked about this back on the slide. We don't have any information to suggest that there's a relationship between the assembly times we have in the two samples. So that leads us to believe that they are independent of one another. The samples are small, less than 30, but we're told we can assume that the populations are normal, and we also are told that we can assume that the population variances are equal. So t-test with equal variances is just another way of saying a pooled variance t-test. All right. Moving on to step 4 of my hypothesis testing procedure, I'm going to state my degrees of freedom, and that is computed by taking the sum of the two sample sizes and subtracting 2. In this case, that gives me 48 degrees of freedom. And then I will compute my critical value of t. Let me blow this up just a little bit here. I'll compute my critical value of t. Because I'm doing a two-tailed test, I split my alpha into 2, and then I will do that. I will find that t value for 48 degrees of freedom. If I look that up in the table, I would be looking up the t value for an upper tail region of 0.025, 1/2 of my alpha value, and 48 degrees of freedom. In the table, that gives me a value of 2.0106. We will look at the Excel spreadsheet in a moment, and there are two functions that I might want to use in Excel to find this t-value, either the t-inverse function or the t-inverse two-tailed function. And like I said, we'll look at that in just a moment. So we'll confirm that 2.0106 value. But knowing that value, I can state my rejection rule that we are going to reject our null hypothesis either if we get a t-statistic, a test statistic, greater than 2.0106 or a test statistic less than negative 2.0106. So just saying what we're going to do once we get our results. Then you're not given data in the problem statement. And actually, let me go ahead and show you the Excel spreadsheet that contains this data. And let's take a look at this. Again, I'll blow this up a little bit. What I'm actually giving you here is the raw observation. So I guess this would be time in minutes maybe to assemble these chairs. But you're actually seeing all 25 observations. Now they're in 2 columns and they're next to one another, but please don't take that to mean that this time of 6.8 minutes is somehow associated with this time of 5.2 minutes. They just happen to both be the first time in their respective samples. So I'm actually giving you the raw data, and let's go ahead and start making a few computations here. Now I've got my labels for the computations already set up. I'm also showing you the formulas over here, and these formulas will they will appear here in column F in the PDF file that I will post in Blackboard for you. I'm actually going to go ahead and create the functions as we go, just so you can see them work. But starting with my raw data, I need to count how many items are in my sample. And so let me go ahead and start with that. I'm going to use the count function, and I will just highlight all 25 items there. And we already know we've got 25, but it's good to confirm that. Then I'm going to go ahead and compute my sample mean, and I can just do that with the average function. And so I can do that if I select the right formula. There we go. Give it my data to work with. And so I can see the average assembly time for method A, 6.288 minutes. Then I'm also going to go ahead and compute the variance. And for that, the function I'm going to use is var.s, variance of a sample, and give that my first 25 assembly times. And so I get a variance of 0.08478. Go through the same process for sample B. My count function will count how many numbers are in the range of cells. My average function will give me the mean of those numbers. And the variance.s function will give me their variance. All right, so the values that I'm seeing here, 25 in each sample, a mean of 6.2880 for sample A, method A, 6.0160 for method B, and then I can also see the variances here. I'm going to just move that over to the side and take a look here, and you can compare and see I just picked up those numbers and recorded them in this table in the write-up for my solution. So same numbers. All right, let's go back to the table here, or to the solution write-up here, and move on. Now, the next computation I need to make is my pooled variance computation. So I've just pulled over the formula we saw on the PowerPoint slide just a moment ago. So you can see sample size minus 1 times the variance of sample A, sample size 2, so on and so forth. Just plugged in the numbers here, and I'm showing you the result. In order to do that computation, again, let's go ahead and we'll go back to Excel and see about making the computation there. Now, certainly you should be able to do this in a calculator, write it out and do it in a calculator if you want to, but I like using Excel for this because I find it actually works nicely. Now, one thing I do like to do is kind of break this computation down a little bit and do it in a few different pieces. And so let's take a look again at this formula. This parenthetical term that starts out this pooled variance function, sample size for A minus 1, that's actually equivalent to the degrees of freedom just for sample 1. And then this parenthetical term, sample size minus 1 for B, is equivalent to the degrees of freedom just for that term. So one intermediate computation I can do, just to keep things fairly simple, is I can compute degrees of freedom for each of the two samples. And that's just a simple subtraction operation. I'll take the sample size of 1, sample A minus 1, and the sample size of sample B minus 1. All right, and so not a hard computation. We can verify those results with a little bit of math in our heads there. But it's nice to have. And then I'll also go ahead and compute my total degrees of freedom. And so for that, I'm just adding those two degrees of freedom for the individual samples together. And what that gives me, if we go back again and look at our variance, is that gives me the parenthetical term, the value for the parenthetical term in the numerator, the two parenthetical terms that I have there, as well as the sum of the two parenthetical terms down here in the denominator. So that lets me simplify things a little bit. If you look over here, 25 minus 1 is 24, like we just computed, times the variance of the first sample, 24 times the variance of the second sample, divide by the sum of the two samples minus 2, which is our total degrees of freedom. So you can see what I've done is I've done some intermediate computations that I can then plug into this formula. All right, let's go back. And now with some of those computations being made, that simplifies entering the formula to compute my pooled variance, because I can take the degrees of freedom for the first sample times its variance, then add degrees of freedom for the second sample times its variance, the variance of sample 2, and then I will close the parenthesis there, and then divide that whole term by the total degrees of freedom. And so if I've done that computation correctly, and I think I have this time, if I've done that computation correctly, that gives me a pooled variance, which you can, again, kind of check intuitively. Let me shrink this down a little bit so I can see a little bit more on the screen. You can kind of check intuitively and see that it's roughly between the two. In fact, actually, it's almost exactly between the two sample variances, because essentially what we've done is computed a weighted average of those two sample variances. All right, so that's our pooled variance. The next thing I want to compute is my standard error. And let's go back and take a look at that computation. The standard error is the term in the denominator. And so to compute the standard error, we take that pooled variance, multiply by 1 over sample size for 1, 1 over the sample size for 2, and then take the square root. So you can see the formula here. I'm going to try and replicate that formula. So I'm going to start with my square root function, and then I'm going to take the pooled variance that I just computed, multiply that times 1 divided by the first sample size, and then add 1 divided by the second sample size. Close the parentheses for the denominator, close the parentheses for the function, and I get a standard error of 0.2933. Okay. All right. So that gives me the standard error. Now, still doing intermediate computations, and I've got a couple of other intermediate computations I want to make here. One is the difference between the two sample means. Let's go back to our write-up. The difference between the two sample means is the term that we see right here, difference between the mean of sample 1 and sample A and sample B. And so that becomes part of the numerator for my test statistic. All right. This is just an easy computation here. I'm taking the mean of sample 1 and subtracting the mean of sample 2. Okay. And so you can see that just comes out to be E12. As part of my starting data, this isn't a computation. This is a value that I had just typed in, but this 0 that you see here up in cell E2, this is what I hypothesized the difference between the population parameters to be. And so again, flip back here, that hypothesized population parameter, or difference between the population parameter, is the other term that we need to compute our test statistic. And normally, as we said before, that's going to be a value of 0, and we can see it there. So I've computed now all of the pieces that I need for my test statistic, difference between my sample means. I entered the hypothesized difference between my population mean, and we just calculated the standard error that goes into the denominator. So now we can verify or go ahead and actually compute the result that we see here, which is the test statistic for this data. So let's come back, and my test statistic is going to be the difference between the sample means minus that hypothesized difference between population means, and then divide by my standard error. And that came out to be 0.9273, which matches the value that we had shown in our results earlier. Now, one thing I could do if I wanted to is, again, we've said that that hypothesized population parameter is almost always going to be 0. I could leave that out. I actually kind of like putting it in there for two reasons. One is that if I leave that in there, then I know that my formula is consistent with what I'm seeing here, so it just helps me make sure everything is lined up. The other reason is if I were to run into a situation where I'm hypothesizing a difference other than 0, then I know I have a formula that's going to work if I were to plug in a different value here. So I like to leave it in. Doesn't make my formula that much more complicated. So there is my test statistic. Now, at this point, because I've already shown you what the critical values of T are, at this point we already know that we are going to fail to reject or not reject this null hypothesis because the test statistic we just computed is not more extreme than our critical values. But I did say that we would see how to find that test statistic in Excel, and that's what I want to do next. So we're going to take this, we're going to use this T inverse two-tailed function. And so coming down here, I've just got a little section where I'm going to compute my upper and lower critical values for the two-tailed test. I'm using the T inverse two-tailed for both of these. This is not the only inverse function I have for the T distribution, but I kind of like this one because to me it's sort of easy to understand in a two-tailed situation. So the arguments that I need to give to this function are the probability, and this needs to be the entire alpha value that I want to use. So the probability that I'm going to use, and then the degrees of freedom for the distribution. So my probability, that's the alpha value that I had entered up above for my level of significance, so I can just plug that in. And then for degrees of freedom, we've actually got a few to choose from here. If you recall, we computed degrees of freedom for each of the two samples, as well as total degrees of freedom. What we need to use here is this total degrees of freedom, which is, in this case, it's 48. And that's because the distribution that we're actually working with here is a distribution of the difference between the population means. And so total degrees of freedom incorporates both of the samples that we're working with. Remember, degrees of freedom is based on sample sizes, and in this case we've got two samples to worry about, and so total degrees of freedom is n1 plus n2 minus 2. And so go ahead and click OK. Now, notice that when I gave the T distribution, when I use that T inverse two-tailed function, it automatically gives me the upper tail distribution. If I actually want the lower critical value, what I can do is I can just put a minus sign in front of that formula there, and that gives me the critical value on the lower tail. Then I can just repeat the process, get that T inverse two-tailed, giving it my alpha value of 0.05 and my total degrees of freedom of 48, and I can get that 2.0106 upper tail critical value. And so that is where the numbers that were stated in my rejection rule actually came from. All right, so knowing that, where all these computations were come from, we can go back and we can verify our decision that we are not going to reject the null hypothesis. 0.9273 is between the two critical values, not more extreme than either one, which tells us that we do not have sufficient evidence to conclude that office chair assembly times are different between the two methods. And so that's our decision here, that we do not reject. And then the following sentence is our managerial conclusion, just interpreting that decision in the context of the problem that we're working in. All right, so going through step 6 here wraps up this first requirement that we're going to test these hypotheses using the critical value approach. The next two steps ask us to find the p-value as well as the 95% confidence interval, and then verify that those two approaches to hypothesis test lead us to the same conclusion, and they should. We should never have a situation where we're getting different results from these different approaches to doing our test. If you do get different results, that's a clue to you that you've made a mistake somewhere. So to compute the p-value, remember that the p-value is based on our sample data, and what it represents is the probability that we could get a test statistic which is at least as extreme as what we got, if in fact our null hypothesis is true. So I've got that stated here. P-value is the probability of getting a test statistic at least as extreme as the one found if the null hypothesis is true. We're doing a two-tailed test in this problem. And so when we compute our p-value, what we have to recognize is that either a test statistic more extreme in the positive or in the negative direction would have caused us to reject the null hypothesis. So when we compute our p-value, what we're doing is we're computing and summing two different probabilities. And those are the probability of getting a test statistic which is greater than what we did, 0.9273, and adding that to the probability of getting a test statistic less than the negative of that value, so negative 0.9273. So upper tail and lower tail probability of getting something at least as extreme as what we got. Now, in order to find a probability associated with a t-statistic, we've got to use an Excel function. The tables in the book are not set up to look up a probability based on a t-statistic, because remember, the way they're set up is the columns are arranged by upper tail areas, and so they're only showing probabilities for those upper tail areas they decided to include in the table. But good news is we've got an Excel function. In this case, I'm going to use the t-distribution two-tailed function, and what I can do is I can give it that t-value, and it's going to tell me the associated probability. So let's go back to Excel, and I'm just going to come down here and find my p-value. And I'm using the t-distribution two-tailed function here. And again, I'm going to search for the functions because I just want to show you. There's a bunch of them available to you. You've got a t.dist, which gives you the lower tail, the area in the lower tail of a t-distribution. You've got t.dist right-tailed, RT, which gives you the area in the upper tail of a distribution. And then you've got t.dist two-tailed, which gives you the sum of the areas in both tails of a distribution. For this one, I'm going to go ahead and use t.dist two-tailed because I'm working with a two-tailed hypothesis test. The value of x that I need to give to it is the t-statistic that we just computed, and degrees of freedom is my total degrees of freedom that we had computed previously. So I'm telling it what this is going to do is it's going to look to a t-value of, where is my t-value, 0.9273. Yeah, we're seeing it right here, 0.9273. And it's going to give me the probability under a t-distribution with 48 degrees of freedom that is greater than positive 0.9273 and then also less than negative 0.9273. And so the sum of those two works out to be 0.3584, and that is the probability, if in fact there is no difference between the assembly times given the two different methods, that's the probability of getting a test statistic at least as extreme, which we could also interpret as the probability of getting a sample difference at least as much as 0.27 minutes between the two assembly times, if in fact there is no difference. And so what that tells us is it's actually pretty likely that we could get a difference that's just over a quarter of a minute if in fact assembly times are equal. 35% chance that we could get a result at least that extreme. And so with a 35% chance, yeah, they're different, but they're not different enough to say that it is statistically significant. Therefore, we do not reject our null hypothesis. And that confirms what we decided in our critical value approach to the testing. The basic rule for interpreting p-values is that if your p-value is less than your chosen level of alpha, you reject the null hypothesis. Otherwise, you do not reject the null hypothesis. Remember that our chosen level of alpha was 0.05, and so 0.35 is definitely not less than 0.05. So that confirms our conclusion. We do not reject. All right, so that's the p-value. The nice thing about p-value is that we interpret it the same way every single time. One-tailed test, two-tailed test, z-test, t-test, f-test, we always interpret the p-value the same way. If you get a very low p-value, less than alpha, you can reject the null hypothesis. If it's more than alpha, you do not reject. All right, last thing I want to do is do our confidence interval. For this, let's go ahead and go back to our slides just for a second because I want to show you the formula for the confidence interval for the difference between two means in a pooled variance situation. And again, this is an expanded version of what we've already seen. And so what we have here is a point estimate. I'm abbreviating here because I don't want to write too much out. What we have here is a point estimate for the difference between the two population means based on our sample means. We are going to add and subtract a margin of error, and this whole term over here is our margin of error. The margin of error is computed by taking a t-value for 1/2 of our chosen level of alpha and multiplying that by the standard error of the distribution. And we've already seen that standard error term when we computed our test statistic earlier, and this is computed the same way. So the standard error is that pooled variance times 1/n1 plus 1/n2. Take the square root of that whole thing, and that's our standard error. Still working with a t-distribution with n1 plus n2 minus 2 degrees of freedom here. So the really good news is that we've calculated almost all of the pieces that go into this formula. We've calculated the difference between the two sample means. We've calculated the standard error. We know what the t-value is, the critical value of t is for 1/2 of alpha with 48 degrees of freedom. All of that's already in our spreadsheet. So this is really just a matter of plugging a few things in to determine the upper and lower limits for the confidence interval for the difference between the two means. So let me go back to Excel, and I can compute my margin of error by taking the upper critical value. I want the positive number just because it's a little easier for the computations, the upper critical value, and multiplying that by the standard error that we had computed above. That gives me a margin of error of 0.5897 minutes, almost 0.6 minutes. And then in order to determine the lower limit of our confidence interval, we are going to take our computed difference between sample means and subtract that margin of error. In order to compute our upper limit for the confidence interval, we take the computed difference between sample means and add the margin of error. And so that gives us a confidence interval such that we can say with 95% confidence the true difference between assembly times for method A and method B is somewhere in between negative 0.3 minutes and positive 0.86 minutes. So because that 95% confidence interval includes the value that we had hypothesized as our population difference, remember we hypothesized a difference of 0, because that hypothesized difference falls within the limits of our confidence interval, that also causes us to not reject the null hypothesis. So difference really could be 0. All right, and the actual difference that we saw, which again was a fairly small difference here of 0.27 minutes, that actual difference is easily attributable to random chance between the two samples. So what we have seen here is that by testing the critical value, or testing our actual test statistic against critical values of t, by computing a p-value and comparing it to our alpha, and by computing confidence intervals and comparing that to our hypothesized difference, we have reached the same conclusion that we will not reject the null hypothesis. We see no difference in assembly times between the two different methods. And so coming back to my write-up, you can see here's plugging the numbers into our formula and then also reporting our p-value differences there. All right, so that is start to finish a pooled variance t-test. I happen to choose a two-tailed set of hypotheses for this example, but I could very easily change that to a one-tailed test. Really, the only thing that would change if I were doing a one-tailed test, my rejection rule would change because I would only worry about rejection in one decision. The way I compute my p-value would change. And let me go back to my write-up here so I can show you what I'm talking about. My rejection rule would change with a one-tailed test because I would only need to go in one direction in order to cause me to reject the null hypothesis. My p-value computation would change because I'd only worry about test results that are more extreme in one direction. And it's possible to use a confidence interval to evaluate a one-tailed test, but it's getting to be a little bit more complicated than I want to get into here. So I'm only going to ask you to do confidence intervals when you're in a two-tailed situation. But I will post just a write-up of an example that gives you a one-tailed test in a pooled variance situation, just so you can see that and have something to refer to. But I'm not going to do another separate video walkthrough with that. So just wanted to point out those things would change. All right, so that wraps up this video. The next one will look at the independent variances version.